function, and given a specific function, which can be as a function of x, y, z, we have to calculate the gradient of the function, and the gradient of the function, it produces a vector quantity, and then, but this gradient, this was equivalent to the maximum change. Actually, when you say maximum change, this would be maximum increase. Okay, so it would include the direction where it was increasing the most and the magnitude. So and then from here from this part we can easily notice how much a certain function is changing in another direction. Okay, so what we needed to do then, it would be that a vector which is gradient of a function f, which is a vector, and this would be equal to the gradient of f. We can find how much this is changing along a different direction just by taking the inner product between the gradient of a function f dot product dl. Okay, where dl, it would be any direction of interest. Okay, so this is what we covered the last time, and then we discussed here in the class. We talked about the divergence theorem and the Stoke theorem. And the divergence theorem and the Stoke one, as we said, we are not going to derive them step by step here together, but we are going to see how we can implement those. Okay, and the divergence theorem, what it included, so we know that for any vector A, we can easily calculate what is the divergence. We can also calculate what is the curl, okay? And from these two mathematical constructs, I like to call them often mathematical constructs, but what they showed was, they both show the divergence and the curl of a vector A, and we can never know everything about a vector if we do not find the divergence and the curl, okay? Because they show different aspects of how a vector quantity changes. And we've noticed in the previous sessions of this course that we have observed that sometimes for a specific vector, we can obtain divergences equal to 0, but curls different from 0, and the other way around, where we could have also vectors whose curl is 0, but divergence is different from 0. For example, electric field has a curl equal to 0. Electric field, because that one, it extends in a straight line from point of source, from the source point, which would be, let's say, a point charge, which is going to produce a vector quantity E, which is the electric field. The curl of that one is equal to 0. In fact, if you go over chapter 2, we also learned that the curl of the divergence of a scalar quantity, it is always equal to 0, because it's simply a vector, a property of the vectors, okay? So, example, we can say this, the curl of E, it's equal to 0, but we'll come back again to this one later. We just wanted to say that vectors can have both the divergence and the curl equal to 0, both different from 0, or either one of those 0 and the other non-zero. Now, the first theorem that we mentioned also last time is the divergence theorem. The divergence theorem, it reports the following. So we can have the divergence of the vector A times d volume. This would be equal to the vector A dot ds, where S is the surface area. Then we can also have the curl of A times ds. This would be equal to the vector A dot dl. This is a closed surface integral, this is a closed line integral. So these are two important theorems that we're going to use a lot. The first one, it is divergence. The second one, it is the Stokes theorem. Now, we can, let's see if we can pick up some examples. Okay. Okay, so let's assume that we have a vector A, which is equal to 2xz plus 3y squared ay plus 4yz squared az. Okay, so this is the vector, and let's check the Stokes theorem for this vector. So let's check the Stokes. Sorry. Let's check the Stokes theorem for the given path. And the path we are going to consider is the following. So here we have the x, y, and z, and we will consider 1, 1, okay, so this is the given path, and we want to check for the Stokes theorem. In fact, what we need to find here is that first of all we have the vector A, and immediately we should be able to calculate what is the curl of A, and also what is the line integral of A along this closed path, okay, which goes from point, let's say from point O, A, B, C, and coming back to point O. Now, the first thing that we should calculate is we should find what is the curl of A. In order to find the curl of A, we have to search for AX, AY, AZ. Here we have the derivative with respect to X, derivative with respect to Y, and derivative with respect to Z. This component is equal to 0. Then here we have 2xz plus 3y squared, and here we get 4yz squared. This part, we find that the component along the AX, this is going to be the derivative of this term with respect to y, okay? So we have to carefully so here we have 4z squared minus 6y, and then for z squared, is it plus y squared? Okay, this is dy. Sorry, we have a mistake here. This should be the derivative with respect to z, because we have the derivative with respect to x, y, and z. And here, then this means that this is going to be 4z squared plus 2x plus 2x, and here we have minus AY. Who can help me here? Is someone? So what should we get here for the AY? So here we have the derivative with respect to x of 4y z squared, so this is 0, minus the derivative of the 0 with respect to z. Then here we have plus az times the derivative of the first term here, so with respect to x, which we're going to have just the 2z. Okay, so this is the curl of A. Now the next step is that we need to identify. So we found the curl of A. Okay. Now the curl of A, we did this. So now we know what this is. The next step is trying to identify what is ds. What is the surface area element? Now this is a vector. Let's do this one a little better. Vector. This is an inner product with ds. Okay. Now the surface area here, the first, we see that it is allocated on the yz plane. If it is on the yz plane, the ds as a vector, this is equal to ax dy dz. Okay. We know this one ax because we can use, we've chosen this convention, we can use the right-hand rule, which states that if we follow the path as it is closed in this direction, we get this direction for the surface area. So we just follow with our fingers along the path L, over which we're going to have also an integral. So that's what we get here. So we know, it looks like we found the curl of A. Now we know what is the ds. And the next step, what we need to calculate is the following, is the curl, this curl, we should take the inner product with this surface area. So we should have the following, the curl of A dot product with ds, and this is equal to ax 4z squared plus 2x plus az times 2z. Now this whole thing, we take the dot product with az, sorry, this is ax dy dz. In this case, since we have a dot product, the only non-zero term, it will be the inner product between these two. Okay? Because the inner product between az and ax will be equal to 0. So in this case, we know that the dot product az and ax, this will simply be a 0. And then you get only the first term, which is different from 0. But you should also notice that this plane right here, it is located when x is equal to 0. So if x is equal to 0, this term will also be cancelled out. And this term, this one, it's equal to 1. So then we are left with 4z squared dy dz. Okay. Then it looks like we found this whole term, okay? Now we need to integrate this one along the x and y, so this is going to change from 0 to 1, and here we get 0 to 1, and 4, it is a constant. We can set here dy, here we can get z squared dz, and the integral of dy, this is, let's write it here, this is 4 times the integral of dy, it is y, from 0 to 1, times z cubed over 3 from 0 to 1 again. The limits of y from 0 to 1, it will simply be equal to 1, so we get here 4 times 1 over 3. So we get here 4 over 3. Now, this 4 over 3, it is this, okay? Now, the next step is that we should be able to calculate, so we found the left side of this identity, of the Stokes theorem, okay? Now, let's try to identify all 4 different paths. The first path from O to A, from 0 to A, let's write it here, from 0 to A. What do we get along this path here? If we move in that direction, what we have is that x is equal to 0 and z is equal to 0, right? I believe this is true because it's easy, but of course it's true, but it is also easy to notice because this is, here we have the y, here we have the z, and along this path we are simply changing the value of y. So this is what we can write here. And along this path, when x is 0 and z is equal to 0, what we observe here is that this term will be 0, this term will also be 0, and the vector A, as long as we are going along this path, it is going to be expressed only as the 3y squared ay, okay? So then we can say that the A.dl, maybe it's good also to notice, probably, let me see for a second. So, dl, this is equal to dy, ay, okay, along this path. Then here, the dl along this path, it is going to be equal to dz az. Okay, so this is how these will be used, and here dl also along this path, it will be the same expression with this. So let me draw it like this. So you get the same expression for dl, and also along this path here and this path, dl will be the same like this. So dl, it will be only the change along the z. So we get here dz as we're moving along this path, dz here, dy here, and dy also here. So then, this means that ADL, it is equal to the 3y squared dy. And then, what we need to do here is that we need to integrate both sides, and the integral is from 0 to 1. And can you calculate this one? What do we get for this integral here? And for this, let me pick you alphabetically. Let's start with Andilika. Andi, can you calculate this integral for the first part from 0 to a? Then Andrea, then Andri, and Arduena. So from A to B, we can say that what is happening from A to B? First of all, x, what is x? Let me ask Andrea. Andrea, what is the value of x if we go from point A to point B? Andrea, probably you are answering the first, this integral here. Andrea, so I have 4 names on the list. I have Andrea, Andreo Shalfi, and Anduena. This question is valid for all these 4. The first 4 according to the alphabet. What is x if we are moving from point A to point B? Can somebody speak? I'm wondering whether my speakers are off. Doe zijn fix box up. Ga de koers doen?
Yes.
Okay. So now, then let's Antonella, Anduena, does your microphone work? X is 0. Yes, Stephen. Thank you, Stephen. So x is 0. That is true. You can also write in the chat section, please. Then if x is 0, what can you say about the y? What is y? Along the same path.
Y is 1.
Okay, that's good. Y is equal to 1. That is true. So then, what is ADL? So we get these examples, but what is A dot DL? Nastasia Barabarka. So x is 0, y is 1. That means that this is, and by the way, let's notice what is DL. Stephen, can you answer this? What is DL from A to B? Stephen? And it's dz az. Wait a second. Yeah, it's this expression. So if this is dz az along this path, when we do the inner product with ADL, with this term, what is the only term that survives? So if we do the inner product between this whole expression here and this DL, we are going to get 4y z squared dz, okay? So that, and by the way, maybe it's best if we erase this completely. And so from A to B, A dot dl, this is simply equal to 4y z squared dz, okay? Because we cannot multiply the az with ax, sorry, with ay, because the inner product will produce a 0. So this ADL, it is equal to, and let's have a look, y is equal to 1. So here we get 4 z squared dz, okay? And please calculate this one also. So we need to integrate now these. Then we have a path B to C. From path B to C, we can check what is x and z. What is x? What is x for the path B to C?
0.
0. Actually, x is always 0. So let's also do this one. From C to the origin, this one here, x, it will still be equal to 0. Then what is z?
Z is 1.
Z is 1. Then here we get x is 0. Wait a second. Yes. And what is y?
Y is 0.
Y is 0. That's good. So these do simplify our expressions considerably, because from B to C, let's do this here. From B to C, A dot dl. So we are moving along this path, and we have the AY. If we have the AY, who can answer this? What is A dot dl? What is it? 2x squared plus 3y. Andrei, can you speak with your microphone?
Just the first expression.
Okay, that's good. So we have this expression here, which is 2xz plus 3y squared. And now this is ay dot ay, so this is going to be dy alone, okay? And then we can simplify this a little further, because x is equal to 0. So we get then 3y squared dy, right? So then here we get integral of a dot dl, and this is 3y squared dy. Similarly, for a path from C to the origin, a dot dl, it is pointing along the AZ, so only this term will survive during the inner product. And here, who can answer this? What is this one? So along this path, when y is equal to 0, this whole thing is equal to 0. So a dot dl is equal to 0, it's equal to 0. Now, if we integrate, I believe we cannot see much more than this. So the first integral here, as you answered, I think Andrea gave an answer for this. Here, we got here 1. This other integral, this is equal to 4 over 3. And this is equal to minus 1. So if we add all these 3 terms, we can say that the a dot dl for this specific case is going to be also equal to 4 over 3. So apparently, we confirm the Stokes theorem for this vector field, which depends on x, y, and z, along this path, okay, or along this closed path, which is enclosing a surface area equal to 1 unit square, 1 centimeter square if the unit is centimeter, or we can simply call it 1 unit square. Okay, so this was the Stokes theorem, and let's see if we can come up with some other interesting example. I think. Let's say this. Divergence of the vector field. Okay, we can move a little further. Okay, so let's define, I'm going to leave these two theorems here on the board because they can lead us, they can help us for the solution. And let's assume that we have a vector A which is equal to the AR times R plus A5 times 0 plus AZ times Z, okay? I just chose to write it this way to remind us that this vector A in the cylindrical coordinate system, apparently it looks like we're in a cylindrical coordinate system where we're talking about distance R, phi, and the distance Z, okay? Then let's not forget that this is equal to, this is AR plus A phi times A phi plus AZ times AZ. So this is the general expression. Okay, so this is how we write any vector in cylindrical coordinate system. And what we are trying to show there is that we have a projection of AR along the R direction, we have a projection of A phi, and so on. So with this definition of the vector A, we can simply write that AR is equal to R, A phi, this is 0, sorry, this is not unit vector, this is a projection, and AZ, it is equal to Z. Now, let me ask you just a flash question, which is the following. If we had a vector B, which is equal to 3AX or 3AR plus 4AZ. Think about for a moment, if we wanted to check the divergence theorem using B. So you can do this one as a homework, but now let's come back to our problem here. So far, we've seen the vector, but let's say that we want to, confirm the divergence theorem for a volume which will be a volume, it will be defined, which is like this. This is X, Y, Z. Okay, so this is let's say the problem, and let's assume that the coordinates 1, 2, 3. This is 3. Let's assume for a moment that this is a volume with a radius R equal to 1 and Z equal to 2. Okay, so what we are dealing with a cylinder which has a radius 1, height 2, and now in order for us to create a better idea, we can ask, we can think ourselves, what is the volume of this cylinder? So somebody can answer, what is the volume of this cylinder? You can see this part. So you're given a cylinder where R, it is from 0 to 1. Phi, it's always, we know it is 0 from 2 pi for sure. and z, it is equal from 0 to 2. So what is the volume? You can also write this one in the chat section. 2 pi, okay. Eva, can you correct your, so the volume, well, is for sure it's going to be the surface of the basis, base RC. Base area, right, times the height, and I think, yeah, you're right, 2 pi, yes, it is pi r squared, yeah, you're right then. Pi times 1 squared, pi r squared times the height 2, so it is 2 pi, that is correct, okay. So this is the volume 2 pi. Now, we have a filling, so this is pi r squared times the height, this is equal to 2 pi. That's good. Now, in order to confirm or to check whether the divergence theorem holds for this vector and for this volume, we need to find, first of all, we need to find the divergence of A. Now, what is the divergence of A? So, for this one, you can open the formula sheet and you can look what does the divergence of a vector field, how does it look like in the spherical coordinate system. So please, you can go to the cover of the textbook or the last page of the textbook where you have the divergence theorem for all different coordinate systems. And if you go there, you're going to find an expression which can be written like this. This is 1 over r times the derivative with respect to r of r times ar, okay? Plus 1 over r, derivative of a phi with respect to d phi, plus, let's take this away, this is not some new information, plus the derivative of az with respect to z, okay? So what we get here is that the AR, so this is the expression, which you can find this one in the formula sheet, okay? So this is what you have, which is a given, and this is, which is also a given. Then we continue here, and this is going to be equal to 1 over r, the derivative with respect to r of r times r, so here we get r squared, okay? A phi is equal to 0, so this one, it will directly go to 0. And then, so let's not write it again, plus the derivative az is equal to z. So we have the derivative of z with respect to z. Then this is equal to, now, what the derivative of r squared with respect to r, this is equal to 2r. Then we divide by r, so here we get 2, plus the derivative of z with respect to z is 1, so this is equal to 3. So the divergence of the vector A is equal to 3. Then we need to check this part of the theorem. So then we just integrate the divergence of A over d volume. This is equal to 3, which is this term, times d volume. 3 is a constant, so we can take it out. The integral over the volume, it's equal to the volume itself. So this is 3 times integral with a differential. They are inverses of each other. So we get here 3 times the volume. So this is going to be equal 3 times 2 pi. This is equal to 6 pi. Okay. So this is what we obtain for this side of the integral. So this expression, it was simply equal to 6 pi. Let's see if we get the same quantity or the same number for the right hand side of this identity. Now, in order to find what is A dot ds, we need to find or to carefully look at and define all the possible surface areas. Now the surface areas for this geometry are the following. Here we have one surface area, which is the top. Then we have the second surface area, which is the side, the side. And here we have also the third surface area, which is the bottom plate. Okay, so these are these, and this is the bottom plate. And then let's see. We have here. So we need to determine what is for the first area. So let's call this one the top of the cylinder, the top side. The top side. What is the ds? ds, in this case, it is simply ds as a vector. This is equal to az times the area. Let's call it like this, okay? And for the side, what is the surface area element along this side? How can we express it? Imagine for a moment that we need to find the surface area of this patch. So let's draw this one in red color, okay? So how can we describe it? So that patch that we showed, which will be something like this. So here we have a cylinder, and we want to find the outer surface area around here. How can we do it? We just try to draw something like this, and the surface area of this unit surface area, it should be equal to this side. So what is this side? How can we write this vertical side, which I draw it in red? What could this be? This side. Say it again.
AY.
Of course, it is AY, but we need to describe it as a length. This is going to be dz, okay? Because in order to describe the surface area or the volumes, we're going to use dx, dy, dz, right? If we are in a cylindrical coordinate system, we have dr, d phi, dz. But this length, so if we come up, thank you for answering, but I believe we can write this one as dz because we're moving along this path by increasing z. Now, what can you say about this, the length of this side? Let me draw this in red. What is this? How large is this side? How can we denote it? Someone can answer this? So let's not forget that we are on the cylinder, but I'm just opening this one to make it easy for me to write it down. So if we're moving along this path, which parameter are we increasing? When we say which parameter are we increasing, say it again.
D phi.
The phi. That's right. And what did you say? R d phi?
No, just D phi.
D phi. That's good. So now let's think for a moment. We have a cylinder here, and we have this side. So we said that this was equal to dz. That is correct. And now this will be d phi. But d phi, this should be meters. This is not meters, this is radians. What should we multiply here?
R.
That's correct. Because depending on how far we are from the z-axis, which is like the origin for the outer side of the cylinder, this is going to be dz times r d phi. That's it. Okay. So the surface area element that we're going to write here. But what is the normal vector? What is the normal vector to the outer surface here, everywhere? You have to choose one. we are in cylindrical coordinate system where we have r, phi, and z. So the normal vectors could be the AR, could be the A phi, and it would also be AZ. Which one are you going to pick?
AR.
AR, that is correct, because it is pointing along the direction where A is increasing. Now, since we're discussing this one, as a reminder, imagine for a moment, if you have a sphere, I know we're talking about the cylindrical coordinate system, but to generalize, if you have a sphere, how can we determine the surface area of a sphere? What is the unit vector which is pointing outwards? What is this?
AR again.
But it is AR, capital R, right?
Yes.
Thank you for confirming. So, because this is cylindrical and the spherical coordinate system, we have r, theta, phi. Then we're going to have AR, A theta, and A phi. Okay, what is AR? It is any vector. These are all ARs. Okay, this is also AR, and right here, this is also AR. For the spherical coordinate system, we're going to erase this one pretty soon. But it was clear here that the surface area for the second side, this is going to be equal to AR. Then this was dz and r d phi. That's perfect, okay? Then we have the third side, which is going to be the bottom. For the bottom side, the surface area ds, this is going to be equal to minus az, okay, dA. Whatever the surface area is. And by the way, the dA, we have not written them precisely, in fact. I can say we have to accept them because the unit surface area element, now we understood how was the size, right? But now for a moment, how can we describe the, let's say this is the top side. What is the surface area element here? The infinitesimally small surface area element, it is going to be something like this. So what is the area of this thing that I've drawn here in the red? This is the radius r, this is the thickness, which is dr, and this dA, in principle, this should be equal to 2 pi r dr. Okay? Because the area around here, it is equal to the perimeter here. Okay, so let's cut this one for a moment. When I say cut, we just cut it and we spread it out. If we spread this out like this will be opened, this will be projected down here. Would you agree? So if we bring this here and this other edge, if we bring it here, what is the surface area of this red line? It is equal to this dimension times this dimension. Productive diffusion. So let's not forget, if the thickness here it was dr, this is also dr, which is here. So this is dr, and the length is 2 pi r. So the length of this perimeter. So this is the surface area element. That's good. That's all we have for the moment. These are the top sides, and then we should now at the top side. What is the vector A? At the top side, the vector A, it is going to be, wait a second, this is for, third, RAR plus 4, yeah. Okay, then let's see here. At the top side, the A, it is going to be equal to R, it is a generalized value, this is AR times R plus AZ times Z. but at the top side, since what did we call? I think the Z, we considered Z2. So this is going to be AR plus AZ times 2, okay? This is how we can describe the A in that at the top side, because as we said, Z is maximum 2. At the second side, at the sides, the A, it can be written equal to, in fact, at the sides, since the radius is considered equal to 1, then here we can simply say that this is going to be AR plus AZ times Z, okay? And then at the bottom, the vector A, it is going to be equal to AR times I. So R, it is changing at the bottom plate, okay? But at the bottom plate, Z is equal to 0, okay? So Z is equal to 0, so that's it. Normally, this would be something plus AZ times equal to 0. So simply, we can consider this one as being equal to 0. And now, at this stage, all we need to do is that we should calculate ds dot dA or let's try this one, A dot ds. So this is going to be equal to AZ, so this is 2 times dA. On the sides, this is going to be equal to ds dot this expression. So somebody can answer, what should we get here? If we do the dot product between A and the ds, so ds, it is AR, okay? So when we do the dot product between ds and A here, this should be the only surviving term, okay? Which means that this will be equal R dz d phi. And let's not forget that R is equal to 1 since we are considering that we are on this outer surface area, right? Where R is a constant value. So please find this. And also, we need to do the inner product between A and the ds. But in this case, what do we observe here? This is 0. That's correct. This is 0. So the integral of 0 is 0. But then we have to integrate these other values. So what is 2 times dA? 2 is a constant. The integral of dA of the top side, this is equal to 2 times the area itself. So what is 2 times area? What is this equal to? What is the top area here? It is pi r squared, right? Top area, it is pi r squared, where r is equal to 1. So it is pi. Then, what do we observe here? What is this r? For the outer surface area, this is equal to, we said that r was equal to 1, right? And then we integrate for z, which is from 0 to 2, of dz. And then we have also the integral of the d phi. The integral of d phi, it is from 0 to 2 pi. So then the integral of dz is equal to z, and this is equal to 2. Then the integral of d phi, it is phi, this is 2 pi. So this is going to be 4 pi. this is 0. So then if we add up all these three contributions, we add these together, what do we get as a total? We get here equal to 6 pi. So apparently, we confirm the divergence theorem that it holds for this vector A and for this enclosed volume as shown on the figure, which has a cylindrical shape. Do you have any question?
No.
No. Okay, thank you.